At first glance, Neptune looks like the quietest world in the solar system. A blue sphere, far from the sun, floating in a cold corner where almost nothing seems to happen. But that calm color is one of the most misleading sights in space. Behind it is a planet with winds faster than sound, storms large enough to swallow Earth, clouds that appear and vanish on a schedule we still do not fully understand, and an interior that may be pushing heat upward from depths no spacecraft has ever touched. Neptune is not just distant. It is active in the dark. And the strangest part is that it should not be this violent. It receives only a tiny fraction of the sunlight that warms Earth. Yet its atmosphere moves with a power that feels almost impossible for a world this far away. So tonight, the real question is not only what Neptune is, it is what Neptune is hiding. Before we begin, if you enjoy calm journeys through space, strange planets, and the hidden forces shaping our solar system, subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. Somewhere on Earth, this video may be playing in the middle of the night. Somewhere else, it may be morning. But all of us are looking toward the same deep blue world. Tonight, you are watching the Space for Sleep channel, talking about Neptune, a planet so far away that sunlight needs more than 4 hours to reach it. A world so cold that the warmth of noon would feel like dim twilight. A place we have visited up close only once. And one of the most terrifying objects in the solar system, not because it is loud or bright or close to us, but because it is almost perfectly silent. Neptune sits at the outer edge of the major planets, more than 30 times farther from the Sun than Earth. In most pictures, it appears smooth and peaceful, like a polished blue stone. That image is part of the reason the planet feels almost unreal. Mars looks harsh, Jupiter looks chaotic, Saturn looks grand and impossible to ignore. But Neptune looks simple. Too simple. Its blue color comes mainly from methane in the atmosphere, which absorbs red light and lets more blue light scatter back into space. The effect is beautiful from a distance, but beauty is a dangerous guide here. Nothing about Neptune's atmosphere is gentle. Beneath that blue shell is a violent weather machine wrapped around an ice giant with no solid surface to stand on. If a spacecraft could somehow descend into Neptune, it would not find an ocean under a sky in the ordinary sense. It would pass through layers of hydrogen, helium, methane, haze, cloud decks, crushing pressure, and deeper regions where the words gas, liquid, and ice become less familiar. Scientists call Neptune an ice giant, but the word ice does not mean frozen snow or a clean sheet of winter frost. In planetary science, it often refers to compounds like water, ammonia, and methane under enormous pressure, behaving in ways that have no comfortable comparison on Earth. The planet is not a hard blue ball. It is a layered abyss. That is what makes Neptune so difficult to understand. The part we can see is only the moving skin of a deeper object. Its atmosphere hides the interior. Its distance hides detail. Its long years slows change into patterns that stretch across human lifetimes. A single season on Neptune lasts more than 40 years, because the planet takes about 165 Earth years to complete one orbit around the Sun. Since Neptune was discovered in 1846, it has completed only one full orbit. That fact alone changes the way we should think about it. On Earth, we can watch weather, seasons, and climate over centuries of records. For Neptune, our real close-up knowledge began in 1989 when Voyager 2 passed by. Modern telescopes have added decades of observations, but in Neptunian time, we have barely watched a fraction of a year. We are trying to understand a planet by seeing a few moments of its life, and those moments have not been calm. In 1989, Voyager 2 became the first and only spacecraft to fly past Neptune. It had already crossed the outer solar system, visited Jupiter, Saturn, and Uranus, and was nearing the end of its planetary mission. By the time it reached Neptune, it was billions of kilometers from Earth. The sunlight around it was weak. The communication delay was long. Every image had to cross an enormous emptiness before arriving back home. Then the pictures came in. Instead of a dead frozen world, Voyager found a planet alive with motion. White methane clouds streaked above the blue atmosphere. Dark storms drifted across the disk. The largest of them became known as the Great Dark Spot, a huge atmospheric vortex roughly comparable in scale to Earth. It looked like a bruise on the face of the planet, a deep shadow moving through a place where sunlight was already faint. For a while, the Great Dark Spot became Neptune's most famous mystery. Then, it disappeared. By the time the Hubble Space Telescope looked for it a few years later, the original storm was gone. That was already strange. Jupiter's Great Red Spot has persisted for centuries, slowly changing but remaining recognizable across generations. Neptune's dark storms behave differently. They appear, travel, change, split, fade, and vanish. Some are tracked by Hubble for a few years. Others seem to arrive with little warning, and then dissolve back into the blue atmosphere. A storm the size of a continent can rise out of Neptune's depths, move across the planet, and disappear before a human child grows into an adult. That is not a quiet world. The more carefully astronomers looked, the more Neptune resisted simple explanations. Hubble has watched dark vortices over several decades, and each one seems to tell us that Neptune's atmosphere is not only active, but unpredictable. In one famous case, a large, dark storm was expected to drift toward the equator and fade away. Instead, it changed direction and moved back north. A smaller, dark feature appeared nearby, possibly a fragment shed from the larger storm, then vanished. That sounds like weather, but it is weather under alien rules. On Earth, storms are fed by warm oceans, sunlight, rotation, humidity, and the shape of land and sea. Neptune has no continents. It has no familiar ocean surface. Sunlight is hundreds of times weaker than it is here. Yet, its atmosphere can build vast vortices and push clouds at extraordinary speeds. Some of Neptune's winds are estimated to exceed 1,200 miles per hour, or about 2,000 kilometers per hour. That is faster than the speed of sound in Earth's atmosphere. The number is almost hard to feel, because no human experience prepares us for wind like that. A powerful hurricane on Earth can tear apart buildings. Tornado winds can throw vehicles, rip trees out of the ground, and turn debris into weapons. Neptune's winds are on another level entirely. They do not move across a city. They circle a planet 4 times wider than Earth. But the terrifying part is not only the speed. It is the energy question. Neptune is extremely far from the Sun. At that distance, sunlight is weak. High noon on Neptune would not resemble a bright summer day on Earth. NASA describes it more like dim twilight. The warm sunlight we take for granted here is roughly 900 times brighter than the sunlight reaching Neptune. So why is Neptune's atmosphere so violent? A world that receives so little energy should, at first, seem sleepy. Uranus, Neptune's near twin in size and composition, appears much calmer in many ways. Yet Neptune has the strongest winds in the solar system. It has visible storms, its cloud bands change, its atmosphere glows with hidden activity. Something inside the planet appears to matter. Deep below the blue clouds, Neptune still gives off internal heat. It is not hot like a star, and it does not shine in visible light. But the planet is not simply a cold ball reflecting sunlight. It is losing heat from within. Heat likely left over from its formation, and possibly shaped by slow processes in its interior. That heat may help drive atmospheric motion, lifting energy upward into a world that otherwise seems too far from the sun to be so alive. This is where Neptune becomes unsettling. The planet is not being powered mainly by the world around it. It may be powered by something we cannot see. Imagine a blue sphere hanging in darkness, almost 30 astronomical units from the sun. From far away, it appears frozen and still. But below the visible atmosphere, energy is moving upward. Above it, winds race faster than sound. Between those regions, storms form and disappear like shadows in a deep ocean. Neptune is not terrifying because it is likely to harm Earth. It is terrifying because it proves how much a planet can hide. For most of human history, Neptune did not exist in our sky as a known world. People could see Mercury, Venus, Mars, Jupiter, and Saturn with the naked eye. Uranus can sometimes be barely visible under dark conditions, though it was not recognized as a planet until the telescope age. Neptune was different. It was found through mathematics. Astronomers noticed that Uranus was not moving exactly as expected. Something seemed to be pulling on it. Instead of seeing Neptune first and then calculating its effect, scientists calculated that an unseen planet should exist. They predicted where it should be, pointed telescopes toward that part of the sky, and found it. In a sense, Neptune entered human knowledge as a disturbance, a hidden mass, betrayed by gravity. That origin story still fits the planet. Again and again, Neptune reveals itself indirectly. Its atmosphere hints at the interior. Its storms hint at unknown energy flows. Its rings hint at invisible shepherding effects. Its largest moon hints at a violent capture. Its weather hints at solar rhythms and deep processes acting together across impossible distances. Neptune is almost never simple evidence. It is a clue. The first clue is distance. Neptune's average distance from the Sun is about 4.5 billion kilometers, or 2.8 billion miles. Light, the fastest thing in the universe, needs more than 4 hours to cross that gap. When Voyager 2 passed Neptune, the signal coming back to Earth carried information from a place so remote that every command and every response belonged to the past. Nothing about exploring Neptune is immediate. A spacecraft cannot be steered in real time like a drone. It must act according to plans sent hours earlier. If something goes wrong, the correction arrives late. Every photograph is a message from deep time, not cosmic time, but human time. A picture of Neptune is already old when it reaches us. This delay matters because it changes the emotional scale of the planet. The inner solar system feels connected. Mars is far but reachable by spacecraft in months. Jupiter is distant, but studied by missions that can still maintain a sense of presence. Neptune feels different. It belongs to the edge of practical exploration. Past it, the solar system opens into the Kuiper belt, the scattered disk, and eventually the long darkness where the sun becomes one star among others. Neptune is the last major planet. After it, the map becomes colder, wider, and less familiar. That position gives Neptune a strange psychological power. It is not simply another world. It is the final giant before the solar system begins to fade into something more like interstellar space. Its orbit marks a boundary in the imagination, even though the real solar system extends far beyond it. The planet itself seems to know this role. It is blue, like Earth, but not welcoming. It has seasons like Earth, but each one lasts longer than many human lives. It has weather like Earth, but with winds that no structure could survive. It has clouds, but they are made of methane ice. It has a moon that looks less like a normal satellite and more like a captured world from the outer darkness. Everything familiar about Neptune comes with a twist. Even its color is not a promise. When Voyager 2 sent back images of Neptune, many people saw a beautiful blue planet and imagined something oceanic. That reaction is natural. Blue means water to us. Blue means sky. Blue means Earth from space. Neptune's blue is colder and more deceptive. The color is tied to methane absorption and atmospheric scattering, not open seas. Under the clouds, the pressure rises until ordinary ideas break apart. A human falling into Neptune would never reach a beach, a surface, or a floor. At first, the upper atmosphere would seem almost empty compared with the crushing depths below. Then, the pressure would climb. Temperature and density would increase. The environment would shift from gas toward fluid-like layers. Molecules would behave under conditions far beyond normal human experience. At some point, the distinction between air and ocean would no longer make sense. The planet is a descent with no landing. That phrase is one of the best ways to feel Neptune. A descent with no landing. On Earth, even the deepest ocean has a bottom. Even a storm passes over ground or water. Neptune's storms do not have that kind of stage. They occur within a vast envelope wrapped around a deep interior. The atmosphere is not a thin layer painted on top. It extends downward and gradually merges with stranger material beneath. This makes the great dark spot even more mysterious. A dark vortex on Neptune is not a hurricane sitting above a warm ocean. It is a structure in a giant atmosphere, perhaps a high-pressure system, perhaps a clearing or darkening in cloud and haze layers, shaped by jet streams, rotation, chemistry, and vertical motion. The darkness may not be an empty hole. It may be a region where deeper, darker layers are revealed, or where aerosols behave differently, or where cloud cover is changed by circulation. Even the darkness is not simple. From far away, the great dark spot looks like a patch. In reality, it may be a window into atmospheric layers we cannot otherwise see. That makes every dark spot feel like a temporary opening in the blue mask. For a short time, Neptune shows us a wound. Then, it closes. Scientists have seen multiple dark spots on Neptune, but they do not last forever. Their birth and death may be part of the planet's larger atmospheric cycle. Some form in one hemisphere, drift, change shape, and fade. Others interact with bright companion clouds, which may form when air is forced upward around the vortex and methane freezes into high-altitude ice crystals. The bright clouds are beautiful in images, but they are signs of violence. On Earth, clouds can look gentle from above. A hurricane seen from orbit can look like a white spiral, elegant and almost silent. Down below, it is destruction. Neptune's white methane clouds may look like soft streaks from space, yet they are being dragged through winds that move with unbelievable speed. A cloud on Neptune is not a decoration. It is a tracer of invisible force. That is how astronomers study the planet. They watch clouds move. They compare images taken years apart. They measure brightness in different wavelengths. They use Hubble, Webb, ground-based telescopes, and the old Voyager data. Each instrument gives a different kind of clue. Visible light shows some cloud and storm patterns. Infrared light reveals other layers, rings, and high-altitude features. Over time, the planet's face changes. Sometimes the clouds seem abundant. Sometimes they almost vanish. In recent years, astronomers noticed something especially strange. Neptune's cloud cover appeared to be linked to the solar cycle. The Sun has an approximately 11-year cycle of magnetic activity, affecting ultraviolet radiation and other forms of solar behavior. At Neptune's distance, the Sun is faint, yet long-term observations suggest that changes in solar ultraviolet light may influence the chemistry and haze that help produce cloud patterns. That detail is quietly disturbing. The Sun is weak at Neptune, but not irrelevant. A planet more than 4 billion kilometers away may still respond to solar rhythms, not in the simple way Earth warms on a sunny day, but through chemistry, haze formation, and delayed atmospheric reactions. Neptune is remote, but it is not disconnected. The solar system remains a single physical environment, even at its edge. This makes Neptune feel less like a lonely object and more like a listening instrument. It hears the sun faintly. It answers slowly. Then, its clouds change. But sunlight alone cannot explain everything. If solar ultraviolet radiation helps shape cloud abundance, internal heat still seems important for the power of the winds and the deep atmospheric motion. Neptune is a place where weak sunlight from above and hidden heat from below may interact in complicated ways. The result is a blue world that looks calm only because we are too far away to see its violence clearly. Distance turns terror into beauty. That sentence applies to much of astronomy. A supernova can look like a jewel in a telescope image. A black hole can be described by a glowing ring. A galaxy collision can appear graceful from millions of light years away. Neptune does the same thing on a smaller scale. Its atmosphere may be one of the most extreme weather systems in the solar system, but from Earth, it is a tiny blue disk. The fear is hidden by scale. If Neptune were closer, it would dominate the night sky. Its blue face would show storms moving across it. Its moons would be visible as points of light. Its rings might reveal themselves as faint arcs. The planet would feel alive, enormous, and dangerous. Instead, it sits so far away that even powerful telescopes struggle to resolve fine detail. So, our imagination fills the gaps. That can be useful, but it can also mislead us. Some people imagine Neptune as a frozen marble. Others imagine a blue ocean world. The truth is stranger than both. Neptune is a dense, massive, rotating ice giant with an atmosphere that can generate supersonic winds, a magnetic field tilted away from its rotation axis, a faint ring system, an active-looking moon, and a history we still do not fully know. It is not one mystery. It is a stack of mysteries. Start with the atmosphere. Neptune's upper clouds are made partly of frozen methane crystals. Methane is the same molecule that helps color the planet, and under the cold conditions high in Neptune's atmosphere, it can condense into icy clouds. These clouds ride the winds, revealing atmospheric bands and jet streams. Some move east, others move west. The planet's rotation is fast, with a day lasting about 16 hours, and that rapid spin helps organize the atmosphere into belts, zones, and streams. A fast-spinning planet behaves differently from a slow one. Earth's rotation helps create trade winds, jet streams, and large-scale circulation patterns. Jupiter and Saturn, rotating even faster, display banded atmospheres and powerful jet streams. Neptune, though smaller than those gas giants, also rotates quickly and possesses a deep fluid envelope. In such a world, motion can become organized into long-lived patterns, with winds flowing around the planet rather than simply rising and falling. Yet Neptune still surprises us. Its winds are not only strong, they are strangely efficient. With so little solar energy, something about the atmosphere allows momentum to build and persist. One possibility is that low friction helps. Without mountains, forests, continents, and solid surfaces, winds can keep moving. On Earth, the surface slows the air. On Neptune, the atmosphere flows over atmosphere. Layers slide, shear, and interact without the familiar braking effect of land. But low friction is only part of the story. A machine still needs energy. That brings us back to the interior. Deep inside Neptune, pressures are immense. The planet likely contains a rocky core surrounded by a mantle rich in water, ammonia, and methane under extreme conditions. Above that, The atmosphere transitions through hydrogen, helium, and methane layers. The details are not directly observed. They are inferred from mass, radius, gravity, magnetic field, temperature, modeling, and comparison with Uranus. No probe has entered Neptune. No lander has touched it. No orbiter has circled it. The only spacecraft that ever saw it up close passed by in 1989 and kept going. That is one of the most important facts about Neptune. Our best direct encounter was a flyby lasting days after a journey of 12 years. Voyager 2 gave us a revolution in knowledge, but it also showed how little we knew. Since then, all close-up study has been remote. Hubble watches from Earth orbit. Webb observes in infrared from its distant position near the Sun-Earth L2 point. Ground telescopes use adaptive optics to sharpen views through Earth's atmosphere. But none of these can replace an orbiter living in the Neptune system for years. The planet is still mostly unvisited. A world can be known by a single flyby, but not deeply known. Imagine trying to understand Earth from one pass through the atmosphere, one set of images, one brief moment over the clouds. You might see a hurricane, a desert, an ocean, and a mountain range. You might measure the atmosphere and identify water vapor, but you would not understand seasons, climate cycles, biology, plate tectonics, ocean currents, or civilization. You would have clues, not a full planet. That is our situation with Neptune. We have clues: a blue disk, a few storms, rings, moons, heat, cloud changes, a strange magnetic field. Each clue points toward deeper complexity. One of the most unsettling clues is Neptune's temperature behavior. Scientists expected seasonal changes to be slow because the planet's year is so long. A season lasting decades should not produce abrupt global changes in only a few Earth years. Yet observations between 2003 and 2020 found unexpected temperature variations. Neptune's stratosphere appeared to cool during part of that period, while the South Pole warmed dramatically later. That does not mean Neptune is warming like Earth. It means Neptune's atmosphere has its own long, strange climate system, and we do not yet understand all of it. A global temperature change of several degrees may sound small if you are thinking about weather on Earth. On a distant ice giant, measured across years in the mid-infrared, it becomes important. It tells scientists that the planet's atmosphere can shift in ways that are faster and more complex than simple seasonal models would suggest. Again, Neptune refuses to be quiet. Clouds disappear, storms reverse, temperatures shift, winds race. The deeper pattern remains hidden. This is why the title of tonight's journey matters. Neptune is hiding something, but that does not mean a monster, a base, or a secret ocean filled with creatures. The real hidden thing is more terrifying because it is physical. Neptune is hiding processes, energy flows, interior structure, atmospheric chemistry, a history of capture and disruption. The kind of hidden truth that can change how we understand giant planets around other stars. Because Neptune is not just a planet in our solar system, it is also a template. Across the galaxy, many exoplanets discovered so far are not Earth-like worlds or Jupiter twins. A huge number fall into categories often described as super-Earths, sub-Neptunes, or mini-Neptunes. These worlds do not exist in our solar system in the same way, but Neptune gives us one of the closest natural laboratories for understanding thick atmospheres, volatile, rich interiors, and planets between rocky worlds and gas giants. If Neptune is stranger than we think, then many distant worlds may be stranger too. That is part of the terror. Neptune is not isolated trivia. It may be a nearby example of a common planetary type. The more we learn about it, the more we understand what other planetary systems might be filled with. Worlds wrapped in hydrogen, worlds with deep volatile mantles, worlds with no true surface, worlds where pressure transforms chemistry, worlds where clouds hide interiors for billions of years. The galaxy may be full of Neptunes. Not exactly our Neptune, but Neptune-like planets in endless variations, some close to their stars, some frozen in darkness, some swollen by heat, some stripped down to cores, some with thick atmospheres hiding everything below. So when we look at Neptune, we are not only studying the eighth planet, we are studying a class of worlds that may be common across the universe, and the closest member of that class is already difficult to understand. That should make us humble. For a long time, planetary science was built mostly on worlds we could see in our own system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each planet became a category in our minds: rocky inner planets, gas giants, ice giants. But exoplanet discoveries broke that simplicity. The universe builds planets in masses, sizes, and orbits that do not fit neatly into our old list. Neptune now sits at the intersection of two kinds of mystery. It is a real place with storms and moons. It is also a clue to planets far beyond our reach. That makes every unanswered question about it more important. Consider the magnetic field. Earth's magnetic field is roughly aligned with its rotation axis, though not perfectly. Jupiter's magnetic field is powerful and more orderly in a broad sense. Neptune's magnetic field is stranger. Like Uranus, Neptune has a magnetic axis that is strongly tilted relative to its rotation axis and offset from the planet's center. This suggests that the magnetic field may be generated not in a central metallic core like Earth's, but in electrically conducting layers within the ice giant's mantle. That is not just a technical detail. It means Neptune's inside may be arranged in a way that produces a lopsided magnetic environment. As the planet rotates, the magnetic field sweeps around in a complicated pattern. Charged particles respond. Auroral processes may occur in unusual ways. The planet's space environment becomes another clue to the hidden interior. Magnetism is a shadow cast by the deep planet. If the field is strange, the inside may be strange too. And the inside is where the most alien physics may be hiding. Under enough pressure, water is not simply water. Ammonia and methane are not just simple molecules. Laboratory experiments and theoretical models suggest that deep inside ice giants, materials can enter exotic states. Scientists have discussed superionic water, electrically conductive fluids, and even the possibility that carbon from methane chemistry could separate under pressure. Popular descriptions often call this diamond rain, though the reality is more complex and still actively studied. The important point is not to imagine Neptune as a glittering treasure chest. The important point is that ordinary molecules may stop behaving in ordinary ways. A world can look like a blue ball from outside, while hiding layers where chemistry, pressure, and electricity combine into states of matter barely present on Earth's surface. That is why Neptune is not only a place for astronomy, it is a natural laboratory for physics, under conditions we struggle to reproduce. The atmosphere is the visible mystery. The interior is the deeper one. The magnetic field is the message escaping from below, and the moons may preserve the violence of Neptune's past. The most important moon is Triton. Triton is not just Neptune's largest moon. It is one of the strangest large moons in the solar system. It orbits Neptune backward, compared with the planet's rotation, a retrograde orbit that strongly suggests it did not form normally around Neptune. Instead, Triton is widely thought to be a captured object, likely from the Kuiper Belt, the vast region of icy bodies beyond Neptune. That single fact changes the story of the entire Neptune system. If Triton was captured, then Neptune once grabbed a world from the outer solar system and forced it into orbit. Such a capture would not have been gentle. It could have disrupted any original moon system Neptune had. It may have scattered, destroyed, or reshaped earlier satellites. The Neptune system we see today may be the aftermath of a cosmic theft. Triton looks calm in still images, but its existence is a sign of violence. Voyager 2 saw a surface unlike any ordinary dead ice ball. Triton is extremely cold, yet it showed evidence of geyser-like plumes spewing dark material upward. It has a thin atmosphere. Its surface appears young in places, suggesting resurfacing. It may contain internal activity driven by tidal heating, radiogenic heat, or other processes. For an object so far from the Sun, Triton is unexpectedly interesting. A captured moon with possible activity orbiting a hidden ice giant at the edge of the major planets. That is not background detail. It is part of Neptune's terror. The planet did not simply form and sit quietly in the dark. Its system may have been rearranged by capture. Its largest moon may be an outsider. Its rings may be remnants, dust, and debris held in delicate patterns. The entire neighborhood around Neptune carries signs of instability. Even the rings are strange. Most people think of Saturn when they hear the word rings. Saturn's rings are bright, broad, and spectacular. Neptune's rings are faint, dusty, and difficult to see. Before Voyager 2 confirmed them, astronomers had evidence from occultations, moments when Neptune passed in front of distant stars and caused brief dips in light. Later observations showed that the rings are not simple perfect bands. Some material appears concentrated in arcs, as if pieces of the ring are clumped in certain regions rather than spread evenly. A ring should smear itself around a planet over time. Neptune's arcs suggest confinement, shepherding, resonance, or other gravitational effects involving nearby moons. The details are still challenging. The rings are not as visually famous as Saturn's, but scientifically they are fascinating because they look unstable and delicate. Neptune's beauty is never clean. Every elegant feature has a complication. The blue atmosphere hides violent winds. The dark spots hide atmospheric depth. The clouds hide chemistry. The magnetic field hides internal structure. Triton hides a captured past. The rings hide gravitational choreography, and the distance hides nearly everything. To feel how extreme that distance is, imagine the Sun from Neptune. It would still be the brightest object in the sky, but it would not feel like our Sun. The disk would be tiny. Its warmth would be negligible. Daylight would be dim. The solar system would feel less like a home and more like a fading empire, with the central star reduced to a brilliant point far away. From that viewpoint, Earth would be invisible to the eye. All human history would be occurring on a speck lost near the Sun. Every city, ocean, forest, argument, memory, and life would be hidden in glare. Neptune does not know we exist. It never needed to. That emotional distance is part of the planet's power. Some worlds scare us because they are dangerous up close. Venus crushes and burns. Jupiter's radiation belts threaten spacecraft. Io erupts constantly. Neptune scares in another way. It reminds us that an enormous planet can exist for billions of years, almost completely beyond human attention, moving through darkness, changing slowly, hiding storms larger than countries, and waiting. Waiting is not the right word scientifically, but it is the right word emotionally. A planet does not wait with intention. It follows gravity, heat, chemistry, and time. Still, to the human mind, Neptune feels like something waiting at the edge. We discovered it late. We visited it once. We know enough to be disturbed, not enough to be comfortable. That is the perfect kind of mystery. Not empty, not fantasy, just incomplete. And incomplete knowledge can be more unsettling than ignorance. Before Voyager, Neptune could be imagined as calm because we lacked detail. After Voyager, We could no longer pretend. The great dark spot, the winds, the clouds, the rings, and Triton all proved that the distant planet was active. The question changed from, "What is Neptune like?" to, "Why is Neptune like this?" That second question is harder. Why does it have such fast winds? Why do dark storms appear and vanish? Why does its atmosphere change temperature unexpectedly? Why did its cloud cover nearly disappear at some times? Why is its magnetic field so tilted and offset? Why did it capture Triton? What did that capture destroy? What is happening in the deep interior? The answer to each question is partial. We have models, observations, and good science, but no single explanation ties everything together neatly. Neptune remains a planet of unfinished sentences. That is why a calm documentary about Neptune can still feel frightening. The fear does not come from exaggeration. It comes from proportion. Neptune is about 4 times wider than Earth. Its mass is about 17 times Earth's mass. Its gravity at the cloud tops is not wildly different from Earth's surface gravity, but the environment below those cloud tops becomes impossible quickly. A person cannot stand there. A probe would be crushed and heated as it descended. The planet has no friendly boundary where exploration becomes simple. Even orbiting Neptune would be difficult. A mission would need to travel for many years, slow down at the right moment, survive the outer solar system, generate power far from the sun, communicate across billions of kilometers, and operate in a complex system of moons, rings, and radiation. Solar panels become less practical so far from the sun. Nuclear power becomes essential. Every kilogram matters. Every maneuver is expensive. This is one reason Neptune has remained underexplored. Not because scientists are uninterested, because the planet is difficult. A Neptune orbiter would transform our understanding, especially if it carried instruments to study the atmosphere, magnetic field, rings, moons, and Triton. Over time, it could watch storms form and die from close range. It could map the gravity field and probe the interior. It could study the rings in detail. It could observe Triton repeatedly, search for changes, and perhaps reveal whether subsurface processes are still active. But until such a mission arrives, Neptune keeps its secrets. Telescopes help, and they have changed the story. Hubble has tracked storms and clouds across decades. Webb has imaged Neptune's rings with remarkable clarity in infrared, giving scientists a new view of faint structures not seen so clearly since Voyager. Ground-based observatories continue to measure temperatures, brightness, cloud patterns, and atmospheric chemistry. Each new observation sharpens the mystery. The planet is not ignored anymore. It is watched. Still, watching from afar is not the same as being there. Imagine observing a hurricane through a keyhole from another continent. You would see movement. You might measure brightness, shape, and speed. But the structure would remain partly hidden. Neptune is worse. We are not watching from another continent. We are watching from the inner solar system across billions of kilometers through instruments that must separate a tiny disk from the darkness. Every clear image feels like a victory. Every detail also reveals how much is missing. The Great Dark Spot revealed one such gap. When Voyager saw it, scientists had only a brief window. They could measure its appearance and motion, compare it with other atmospheric features, and use it to infer wind speeds. Then, Voyager moved on. The storm vanished before Hubble could examine it in the same way. A planetary feature as large as Earth became a historical event, not a continuing object. That is almost poetic. A storm big enough to define a planet's image came and went between visits. Since then, other dark spots have appeared. Hubble found new ones. They formed in different hemispheres, drifted, changed, faded. Neptune became a gallery of temporary shadows. Some dark spots may be anticyclones, systems of high pressure rotating in the atmosphere. Their dark appearance may involve changes in aerosols or cloud layers. Their bright companion clouds suggest vertical motion around them. Yet a basic question remains. Why does Neptune make them at all? Deep atmospheric dynamics may be involved. Jet streams can create regions where vortices persist. Methane condensation can affect cloud formation. Internal heat can drive convection. Solar ultraviolet radiation can influence haze chemistry. The planet's rotation shapes large-scale flows. But combining all these ingredients into a predictive model is extremely difficult. On Earth, weather prediction is hard even with satellites, aircraft, ocean buoys, weather stations, and constant data. Neptune gives us a tiny disk and patience. That contrast should make us careful. A confident explanation can sound satisfying, but a planet like Neptune punishes simplicity. Its behavior likely emerges from several linked systems rather than one cause. The interior supplies heat. The sun influences upper atmosphere chemistry. Methane changes phase. Winds shear around the planet. Vortices form in certain latitudes. Haze layers alter brightness. Seasonal geometry changes slowly. Observational limits complicate the picture. Neptune is not a puzzle with one missing piece. It is a puzzle where the pieces change shape. Part of the difficulty comes from scale. A storm on Earth can be studied by flying through it, sampling it, imaging it constantly, and comparing it to thousands of previous storms. A dark spot on Neptune may be seen only in a handful of images across months or years. Scientists must infer the unseen vertical structure from brightness, color, wavelength motion, and models. The storm is three-dimensional. The image is almost flat. That is true for much of astronomy. We observe light and infer worlds. Neptune reminds us how powerful and fragile that method can be. A blue disk becomes an atmosphere. A dark patch becomes a vortex. A bright streak becomes a methane cloud. A thermal measurement becomes a temperature trend. A wobble becomes a moon. A faint arc becomes a ring. We build reality from signals. Sometimes the signals are enough. Sometimes they tease us. Neptune has been teasing astronomers since before its discovery. The irregular motion of Uranus pointed toward it. But that same story also led to later searches for other unseen planets. Some were wrong. Some predictions failed. The outer solar system became a place where mathematics, observation, and imagination wrestled with each other. Neptune was the great success, a planet found because gravity gave it away. But gravity only revealed its location. The planet itself remained mostly unknown. Even after discovery, Neptune was a small telescopic disk. Its moon Triton could be observed, its orbit measured, and its existence confirmed. But the planet's weather, rings, and smaller moons were hidden. Generations passed with Neptune as a distant name rather than a detailed world. Only in the space age did that change. Voyager's flyby was brief, but it turned Neptune from a dot into a place. That transformation is worth slowing down for. Before 1989, many textbook images could not show Neptune's true personality. After Voyager, the planet had a face. Blue atmosphere, white clouds, great dark spot. It also had a system. Rings, moons, and especially Triton. For the first time, scientists could see that Neptune was not just a mathematical endpoint. It was an active world. And then, almost immediately, it became distant again. Voyager continued outward. The spacecraft did not stop. It could not stop. The geometry of its mission allowed a flyby, not orbit insertion. To enter orbit around Neptune, a spacecraft would need to slow dramatically, requiring fuel or clever mission design. Voyager was built for reconnaissance. It revealed the planet, then left it behind. That leaving matters emotionally. Humanity reached Neptune once, looked closely, and kept going. Since then, the planet has remained in our telescopes, but no spacecraft has returned. The only close-up images are relics from a single encounter. Every time we study them, we are looking back to a few days in 1989. Neptune's modern mystery is built on old light and new instruments. The old light came from Voyager. The new instruments are Hubble, Webb, and giant observatories on Earth. Together, they show a planet that does not sit still. This is where the phrase "hiding something" becomes more precise. Neptune hides not one secret object, but a hidden engine. The visible atmosphere is the output. The engine is deeper. Internal heat, rotation, composition, convection, magnetic generation, chemistry, and perhaps the legacy of formation. We can see the smoke, not the machinery. A good analogy is a locked building at night. From outside, you might see lights flicker behind windows. You might hear machines working through the walls. You might see steam rising from a vent. Those signs tell you something is happening inside, but they do not show you the system directly. Neptune is that building. The storms are the flickering lights. The winds are the machinery. The magnetic field is the hum in the walls. Triton is the broken lock that suggests a violent past. And the rings are debris still circling the scene. The more we learn, the harder it becomes to call Neptune simple. Its atmosphere contains hydrogen and helium, like the larger giant planets. But methane plays an outsized role in its appearance and cloud formation. Higher in the atmosphere, ultraviolet light from the sun can break apart methane molecules, leading to more complex hydrocarbons and haze. Deeper down, temperatures and pressures change the chemistry again. At different levels, different substances condense, evaporate, mix, and settle. The clouds we see are only one layer of a vertical story. Above them, haze can affect color and brightness. Below them, deeper cloud decks may exist, possibly involving compounds like hydrogen sulfide, ammonia, or water under conditions far from familiar weather. Below that, the atmosphere merges into the deep interior. Each layer can influence the next. On Earth, weather and climate depend on vertical structure. Warm air rises, water vapor condenses, clouds form, storms release heat, jet streams steer systems, and the surface modifies everything. On Neptune, the players are different, but the idea of layered interaction remains. Methane condensation, haze chemistry, internal heat, and rotation may combine into a weather system that is both recognizable and alien. Recognizable because it has clouds and storms. Alien because the materials, pressures, and scales are wrong for our instincts. One of the most common mistakes is to imagine Neptune's winds as if they were blowing across a surface. In reality, they are part of an atmosphere wrapped around a deep, fluid planet. The wind speeds are measured by tracking clouds at certain levels, not by planting a weather station on the ground. Different depths may move differently. A cloud feature can reveal the flow of one layer while hiding another. This is why Neptune's wind profile is a major subject of study. Some winds move in the direction of rotation. Others move against it. Speeds vary with latitude. The planet's equatorial regions and mid-latitudes can behave differently. Such patterns may reveal how momentum is transported through the atmosphere, how deep the winds extend, and how energy moves from the interior toward the visible cloud tops. A wind map is not just weather. It is a fingerprint of the hidden planet. That fingerprint becomes even more interesting when compared with Uranus. Uranus and Neptune are often called twins, but that word hides important differences. They are similar in size and composition, yet their atmospheres and internal heat appear different. Uranus is tipped dramatically on its side, has extreme seasons, and historically seemed to release much less internal heat. Neptune, farther from the Sun, is more meteorologically active. Why? No simple answer satisfies every observation. Maybe the planets formed differently. Maybe a giant impact changed Uranus. Maybe their interiors are layered in different ways. Maybe heat escapes more efficiently from Neptune. Maybe composition, mixing, and thermal history vary between them. The comparison matters because two planets that look similar on a chart may evolve into very different worlds. That lesson applies beyond the solar system. Exoplanets with similar masses and radii may hide different atmospheres, interiors, and histories. Neptune and Uranus are nearby proof that size is not destiny. Each layer makes the simple name less simple. By now, the blue planet should no longer feel quiet. It should feel like a closed door, and behind that door, several things are moving. The atmosphere is moving horizontally at extreme speed. Heat is moving upward from the deep interior. Chemistry is moving methane through light, haze, and ice. Storms are moving across latitudes, sometimes following expectations, sometimes breaking them. Moons are moving through a system shaped by capture and gravity. Dust is moving through faint rings and arcs. Time itself is moving slowly, because a Neptunian year is longer than the entire span between the American Civil War and the present day. Human observation is brief. Neptune's processes are long. That mismatch creates uncertainty. We may be seeing Neptune during one particular atmospheric phase and mistaking it for normal. Or we may be seeing a normal phase and not yet knowing how it fits into a centuries-long pattern. If clouds fade for a decade, is that unusual? If a dark spot forms, is that common? If the South Pole warms, is that seasonal, chemical, dynamic, or some combination? We do not have centuries of detailed data. We have fragments. A planet can hide in fragments. This is especially true for long seasonal cycles. Neptune's axial tilt is similar to Earth's and Mars's, so it has seasons. But because its orbit is so long, each season lasts more than 40 Earth years. A person could be born, grow old, and die during one Neptunian season. The planet's atmosphere may respond to sunlight, with delays, feedbacks, and chemistry that unfolds slowly. Yet some observed changes seem surprisingly fast. That combination is important. Slow forcing can produce sudden responses in complex systems. A small change in sunlight or chemistry can push an atmosphere past a threshold. Clouds may form rapidly once conditions are right. Haze production may increase after ultraviolet exposure. A vortex may become visible when cloud layers thin. Temperature patterns may shift as circulation changes. Neptune's weather might not be random. It may be organized by rules we have not watched long enough to decode. That is more frightening than chaos. Chaos would mean no pattern. A hidden pattern means the planet is saying something, and we do not yet speak the language. Think again about the disappearing clouds. For years, Neptune showed changing cloud activity. Then, observations suggested that the cloud abundance dropped dramatically, especially after 2019, with only certain regions retaining clouds. Researchers connected long-term cloud variations with the solar cycle, implying that even at Neptune's distance, solar ultraviolet radiation might influence photochemistry enough to change the planet's appearance. A distant blue world becomes a detector of the sun's magnetic heartbeat. The sun sends a faint ultraviolet rhythm outward. 4 billion kilometers away, Neptune's atmosphere may respond by building or reducing clouds. The response is not immediate in the way our skin warms under sunlight. It is mediated through chemistry, haze, and time. Still, the link suggests that the outer solar system is more connected than it looks. The edge is not separate. The sun still reaches it. But because the sunlight is weak, every response raises another question. Why is the response strong enough to notice? What parts of the atmosphere amplify the signal? How does it interact with internal heat and circulation? Why do some clouds survive while others fade? How much of what we see is chemistry and how much is dynamics? There is no single clean answer waiting at the surface. The surface does not even exist. Instead, the answer is hidden in depth. To understand Neptune properly, scientists need vertical information. They need to know what happens at different altitudes and pressures. Which clouds form where? How deep do the winds go? Where is methane abundant or depleted? How does heat rise? How are aerosols produced? What layers generate or suppress convection? How does the magnetic field connect to the interior? Remote observations can probe some of this. Different wavelengths see different depths. Infrared measurements can reveal temperatures and composition. Radio observations can help constrain deeper atmospheric properties. Occultations, where starlight or spacecraft signals pass through an atmosphere, can reveal pressure and temperature structure. But a dedicated mission would change everything. A probe descending into Neptune's atmosphere could measure directly what telescopes infer indirectly. It could sample composition. It could measure temperature, pressure, winds, and clouds with altitude. It could tell us whether our models are close or badly incomplete. Even one probe would be priceless. The problem is survival and delivery. Neptune is far away. Entry would be extreme, and transmitting data from a descending probe through that environment would be difficult. Yet, the scientific payoff would be enormous. A single vertical profile could reshape models of ice giant atmospheres, and ice giants may represent one of the most common planetary families in the galaxy. This is why Neptune deserves more attention than it gets. Jupiter and Saturn are spectacular and closer. Mars is tied to human exploration dreams. Europa, Enceladus, and Titan capture the imagination because they may have oceans, chemistry, or habitability. Neptune feels remote and abstract, but scientifically, it may be one of the keys to understanding planets as a whole, especially because our solar system has only two ice giants. Uranus and Neptune are not extras. They are the only local examples of an entire planetary class. Ignoring them leaves a hole in our understanding. That hole matters when we look outward. Telescopes now find planets around other stars by watching starlight dip during transits, measuring gravitational tugs, imaging young worlds, and studying atmospheres when possible. Many of those planets have sizes between Earth and Neptune. Some may have thick atmospheres. Some may be water-rich. Some may have lost gas over time. Some may be mini Neptunes close to their stars, transformed by radiation. Our own Neptune helps anchor those interpretations. If we misunderstand Neptune, we may misunderstand countless exoplanets. That makes the hidden interior of Neptune more than a local mystery. It becomes a cosmic reference point. How do volatile-rich planets form? How do they migrate? How do they keep or lose heat? How do their atmospheres evolve? What determines whether a planet has a visible surface, a deep envelope, or a thick hydrogen layer? How do magnetic fields arise inside them? The blue planet at the edge becomes a Rosetta Stone, but the stone is partly buried. This is where the emotional tone shifts. At first, Neptune is terrifying because of winds and storms. Then, it becomes terrifying because of distance. Then, more quietly, it becomes terrifying because of ignorance. Not total ignorance, but the scientific kind. A map with borders, measurements, and labels, yet large blank areas in the center. The blank areas are not empty. They are waiting for instruments. Or perhaps better, they are waiting for us to become patient enough to reach them. Neptune does not change quickly. For our convenience, it does not offer close access. It does not glow brightly. It does not reveal its interior. It forces science to work across distance and time. That is why every new observation matters. A dark spot reversing direction, a temperature trend, a cloud cycle, a ring image, a spectral measurement of a moon, all become pieces of a long investigation. The investigation is still young. One full Neptune year has passed since discovery. One spacecraft has flown by. No orbiter has arrived. No atmospheric probe has descended. No lander ever will, because there is nowhere solid and gentle to land. For a planet this massive, that is a strange level of mystery. Imagine if Earth had been seen only once by a passing probe, then watched from far away for a few decades. Imagine aliens trying to understand lightning, oceans, forests, seasons, volcanoes, and life from a single flyby and a tiny distant disk. Their science might be brilliant, but their knowledge would still be incomplete. That is us, with Neptune. This is where Neptune's terror becomes intellectual instead of visual. The planet is not only a stormy blue giant, it is a reminder that reality can remain hidden, even when it is in our own solar system. We do not need to travel to another galaxy to find mystery. We do not even need to leave the Sun's family. At the edge of the major planets, there is a world we still cannot fully explain, a world that looks simple in photographs, a world that becomes stranger with every measurement. That is the first half of the Neptune story. Not a complete answer, a door opening, and behind that door, the next questions are even darker. Because the more we study Neptune, the more it stops being only an ice giant and starts becoming a warning about planets everywhere. They can look calm, appear familiar, fit neatly into a category, and still hide systems powerful enough to break our expectations. In the second half, we have to go deeper, down into the dark spots, into the vanishing clouds, into the captured moon, into the rings, into the future of Triton, and into the reason Neptune may be one of the best clues we have for understanding the hidden planets scattered across the galaxy. Not because they are the easiest part of Neptune to explain, but because they show the problem better than almost anything else. A dark spot on Neptune looks simple at first. In a photograph, it can appear like a bruise pressed into a blue world, a shadow floating across a frozen planet. Yet that small dark shape is not a solid object, not a crater, and not a stain on the surface. Neptune has no solid surface in the way Earth has one. The spot is weather. It is motion. It is a deep atmospheric system exposing how violent and unstable this planet really is. When Voyager 2 flew past Neptune in 1989, one of its most famous discoveries was the Great Dark Spot. It was enormous. It sat in Neptune's southern hemisphere and seemed, at first glance, like Neptune's answer to Jupiter's Great Red Spot. That comparison was tempting. Both were giant storms on giant planets. Both were large enough to make Earth feel small. Both turned a distant world into something with a face. The resemblance did not last. Jupiter's Great Red Spot has survived for centuries. It has changed shape, color, and size, but it has remained an enduring feature in the atmosphere. Neptune's Great Dark Spot behaved differently. When Hubble looked for it only a few years later, the storm was gone. A feature that had looked massive enough to define the planet had vanished into the blue atmosphere, leaving no permanent mark behind. That is the first terrifying thing about Neptune's weather. It can build storms on a planetary scale, then erase them before human science has time to understand them. A storm the size of a world can appear, drift, distort, and disappear. New ones can form in other latitudes. Bright methane ice clouds can gather around them like white scars. The atmosphere can rearrange itself so quickly that a planet photographed in one decade may not look like the same planet in the next. This is not gentle weather. It is not a slow blue ocean of gas. Neptune's atmosphere behaves like a machine with hidden gears, and we have only seen the top of it. The dark spots are usually described as vortices. That word can sound clean and technical, but the real picture is more disturbing. A vortex is a rotating atmospheric system, a region where air is moving around a center, shaped by pressure, temperature, chemistry, and planetary rotation. On Earth, powerful vortices can become hurricanes. On Neptune, the environment is stranger, colder, deeper, and less familiar. The winds do not blow over land or ocean. They move through layers of hydrogen, helium, methane, and deeper materials under pressures we cannot walk into, touch, or sample directly. A dark vortex on Neptune may open a window into lower layers of the atmosphere. It may be surrounded by bright clouds because gases rise, cool, and freeze into methane ice crystals. In ordinary language, that means a dark spot may not simply be a black storm. It may be a place where the atmosphere is arranged in such a way that deeper, darker layers become visible, while bright frozen clouds form around the disturbance. A planet almost 3 billion miles from the Sun is making clouds from methane ice around enormous storms. That sentence sounds unreal, but it is not fantasy. It is Neptune. The more carefully scientists watch the planet, the less stable it seems. Hubble has seen dark features come and go. Ground-based telescopes, using adaptive optics, have tracked bright cloud systems. Webb has shown Neptune and its rings in infrared light with a clarity that Voyager could never provide from Earth. Each instrument adds something, but none has removed the deeper mystery. They show changes. They reveal patterns. They prove Neptune is alive with motion. What they do not yet provide is the complete engine underneath. One reason this is so difficult is that Neptune is not lit and heated like Earth. Our weather depends heavily on sunlight. The sun warms the ground and oceans unevenly. Air rises, pressure changes, storms form, seasons shift, water evaporates, clouds build, and winds respond. Even on Jupiter and Saturn, sunlight plays a role, though their internal heat also matters. Neptune is different because it sits so far out that sunlight is almost an afterthought. High noon on Neptune is not like noon on Earth. It is more like a dim twilight. The sun is still there, but it looks small. Its light is weak. Its warmth is faint. Yet the planet has some of the fastest winds in the solar system. That mismatch is unsettling. Weak sunlight should make a quiet world easier to imagine. A distant planet should seem cold, slow, and nearly asleep. Instead, Neptune contains winds faster than sound, storms that appear and vanish, clouds that can change dramatically, and an atmosphere that refuses to behave like a frozen dead sphere. The answer must involve internal heat. Neptune radiates more energy than it receives from the sun. Somewhere beneath the visible clouds, the planet is still leaking warmth from its formation and from processes inside its deep interior. That heat rises through layers we do not fully understand, feeding motion above it. The Sunday may light the top of the atmosphere, but Neptune is not powered only from above. A buried source of energy is pushing upward from below. This makes Neptune feel less like a planet merely sitting in darkness and more like a covered furnace hidden at the edge of the solar system. The furnace is not hot in the way a star is hot. Neptune is still cold by human standards. Its upper atmosphere is brutally frigid. The word furnace here means something more subtle, an internal energy imbalance, a deep reserve of heat, a slow leak from the planet's interior into a sky where sunlight barely reaches. That quiet upward flow may help explain why the atmosphere remains so active when simple intuition says it should be calm. Even that explanation is incomplete. Uranus, Neptune's near twin in size and composition, does not radiate internal heat in the same way. Uranus appears much quieter in some respects, as if something in its past changed its interior or blocked its heat from escaping. Neptune, by contrast, remains vigorous. Two ice giants, similar from a distance, behave very differently when examined closely. That difference is one of the reasons ice giants are not just larger versions of Earth or smaller versions of Jupiter. They are their own category of mystery. Neptune's atmosphere also carries another surprise, one that sounds almost impossible when first heard. Its clouds may be linked to the solar cycle. At first, that seems wrong. The solar cycle is an 11-year rhythm in the activity of the sun. Sunspots rise and fall. Solar ultraviolet radiation changes. Earth's upper atmosphere responds. Space weather changes around our planet. But Neptune is so far away that sunlight there is only a tiny fraction of what Earth receives. Why should the farthest major planet care about subtle changes in the sun? Yet long observations from Hubble, Keck, and other telescopes have shown a connection between Neptune's cloud abundance and the sun's cycle. The effect is not instant. The chemistry takes time. A stronger period of solar ultraviolet radiation may trigger reactions high in Neptune's atmosphere, and after a delay, the number of high-altitude clouds can increase. Later, as the cycle changes, the clouds can fade again. That is deeply strange. Neptune is internally active, but it is not cut off from the sun. Even at the edge of the major planets, solar radiation can leave a fingerprint on the weather. A distant star, reduced to a small bright dot in the sky, can still alter the face of a world almost unimaginably far away. Then came the cloud disappearance. Around the late 2010s and early 2020s, Neptune's cloud cover dropped dramatically. The planet became darker in some observations because the bright reflective clouds that had decorated its disk faded away, especially at mid-latitudes. The change was not a tiny adjustment. Astronomers described it as surprising because cloud activity fell quickly and stayed low longer than expected. A calm, blue planet suddenly looked emptier. That should not sound terrifying in a dramatic horror sense. No ocean rose, no city was destroyed, no creature moved beneath the clouds. But for a scientist, it is a different kind of fear. A world that seemed predictable enough to be monitored from afar did something large, visible, and not fully explained. The face of Neptune changed, and the reason involved a mixture of sunlight, chemistry, internal weather, and time delays that are still being studied. This is why Neptune is hiding something. Not a monster, not an alien base, not a secret ocean we can point to with confidence. It is hiding the full system of causes beneath the visible image. The blue disk is only the surface of the story. Below the clouds, the atmosphere thickens, pressure climbs, temperature changes, chemistry shifts. Molecules that are familiar in a laboratory become part of a planetary interior no human instrument has directly entered. The deeper we imagine descending, the less useful ordinary language becomes. On Earth, a sky sits above a surface. On Neptune, there may be no sharp surface at all. The upper atmosphere gradually becomes denser and hotter with depth, transitioning into strange fluid layers. The planet is called an ice giant, but that name can be misleading. It does not mean Neptune is a frozen ball of solid ice. In planetary science, ice refers to compounds like water, ammonia, and methane, materials that were ices in the cold outer solar nebula. Inside Neptune, under immense pressure, those materials would not behave like ice cubes in a freezer. They may become exotic fluids. They may conduct electricity. Their structure may change in ways that create a magnetic field unlike Earth's. Neptune's magnetic field is one of the strangest parts of the planet. If you imagine a simple bar magnet running through the center of Earth, you get a rough picture of our planet's field, though reality is more complicated. Neptune does not follow that simple pattern. Its magnetic field is strongly tilted relative to the planet's rotation axis and offset from the center. Uranus has a similarly strange magnetic field. That may mean the magnetic field is generated not in a deep central core, but in a shell or layer inside the planet, perhaps where conducting fluids circulate under extreme pressure. This matters because a magnetic field is not just a decoration, it is a clue to the hidden interior. We cannot see Neptune's deep layers directly, but their motion may reveal itself through magnetism. The field becomes a shadow cast by invisible currents inside the planet. So the terrifying part is not simply that Neptune has fast winds, it is that the winds are only one expression of a deeper machine. The clouds are another. The storms are another. The magnetic field is another. Each is a clue pointing downward toward a structure we still cannot map clearly. A planet can be photographed and remain unknown. That idea becomes even stronger when we leave the atmosphere and look at Neptune's largest moon. Triton should not be there in the ordinary way. Most large moons orbit in the same direction their planet rotates. That makes sense if they formed from a disk of material around the planet. Triton does the opposite. It moves around Neptune in a retrograde orbit, against the planet's rotation. That strongly suggests it did not form as a normal Neptunian moon. It was likely a captured object, a world from the outer solar system seized by Neptune's gravity long ago. The capture of Triton was probably violent on a planetary scale. A large moon does not simply drift politely into orbit. Energy has to be lost. Orbits have to change. Other moons may have been disturbed, destroyed, or thrown away. Neptune's original satellite system may have been rearranged by Triton's arrival. What we see today could be the aftermath of a gravitational crime scene. Triton itself is astonishing. Voyager 2 found a surface colder than almost anywhere else in the solar system, around -235 degrees Celsius. Nitrogen frost covers much of the moon, giving it a bright, icy surface. A thin atmosphere clings to it, made mostly of nitrogen with traces of methane. At such temperatures, the word atmosphere almost feels fragile, like a ghost of air rather than a sky. And then, Voyager saw geysers, a captured moon, far from the sun, locked in deep cold, was still active. Dark plumes rose from the surface, carrying icy material upward. Triton was not dead. It was one of the few bodies beyond Earth known to show active geological behavior. That single fact changes the way Neptune feels. The planet is not only hiding weather, its largest moon is hiding internal processes too. Think about what that means. At the edge of the major planets, where sunlight is faint and temperatures are brutal, a moon can still produce eruptions. The source may involve seasonal heating of surface ices, internal heat, or complex interactions between sunlight and frozen nitrogen. Whatever the details, Triton is not merely a frozen stone. It is a world with activity, history, and a future. That future may be dark. Because Triton orbits backward, tidal interactions with Neptune are slowly changing its path. Over extremely long timescales, Triton is expected to move closer to Neptune. Eventually, depending on the details, it may be torn apart by tidal forces or collide with the planet. If it breaks apart before impact, Neptune could gain a massive new ring system formed from the remains of a captured world. If it falls inward more directly, the event would be catastrophic beyond human scale. This will not happen soon. It is not a future any human civilization is likely to witness, but in cosmic terms, it means Neptune's system is not finished. The story is still unfolding. A moon captured in the ancient past may someday be destroyed by the planet that captured it. That is the kind of tragedy only gravity can write. Triton also raises a wider question. If Neptune captured a Kuiper Belt object large enough to become its dominant moon, then the outer solar system was once far more chaotic than it appears today. Worlds moved, orbits changed, giant planets migrated, small bodies were scattered. Some were captured, others ejected, and many still orbit in the cold beyond Neptune. The neat classroom diagram of the solar system hides a violent history. Neptune's position at the edge of the major planets makes it a kind of boundary marker. Inside its orbit, the planets are familiar enough to appear in every schoolbook. Beyond it lies the Kuiper Belt, a vast region of icy bodies, dwarf planets, and leftovers from the solar system's formation. Pluto is there. Many smaller worlds are there. Triton may have once belonged to that population before Neptune took it. So Neptune is not just the last major planet, it is the gatekeeper of a colder, older archive. A probe orbiting Neptune would not only study a blue planet, it would study a captured moon, a damaged satellite system, rings that refuse to behave simply, a magnetic field shaped by unknown interiors, and a connection to the larger outer solar system. One mission could touch several mysteries at once. But no such orbiter has arrived. Voyager 2 gave us a magnificent glimpse, then left forever. Since then, the story has been reconstructed through telescopes and patient observation. Hubble watches cloud changes from Earth orbit. Keck and other observatories sharpen Neptune through the blur of our atmosphere. Webb looks in infrared, revealing rings and moons in a new way. These observations are powerful, but they are still remote. They are like studying a storm through a keyhole. The rings make that keyhole even stranger. Neptune has a ring system, but it is not like Saturn's bright, obvious disk. Neptune's rings are faint, dusty, narrow, and difficult to see. They were suspected before Voyager, and then confirmed in detail during the 1989 flyby. Later, Webb captured them with remarkable clarity, showing that the planet's ring system had not stopped surprising us. The most peculiar pieces are the arcs. In a normal ring, particles orbit the planet and gradually spread around the orbit. If material starts clumped in one region, orbital motion tends to smear it out over time. Neptune's outer Adam's ring contains arcs, places where material remains concentrated instead of being evenly distributed. The names sound almost poetic. Liberté, Egolite, Fraternite, Courage. Yet the physics behind them is not poetic at all. It is a problem of gravity, resonance, dust, collisions, and confinement. Why do the arcs persist? Why do some fade? How are they replenished? What role does the moon Galatea play in holding them together? These questions sound small compared with storms the size of Earth, but they reveal the same larger theme. Neptune's system contains structures that should be temporary, yet remain visible long enough to challenge simple expectations. A ring arc is a quiet mystery. It does not roar. It does not flash. It circles the planet in darkness, a thin concentration of dust and debris that should be spread out more evenly. Its existence tells us that something is sculpting it. Gravity is doing artwork at the edge of the solar system. The rings also remind us that Neptune is not isolated. Small moons move near them. Dust is produced, shifted, trapped, and lost. Micrometeoroids strike surfaces. Particles collide. Resonances tug material into patterns. Seen from far away, Neptune may look like a lonely blue sphere. Up close, it is a system. Planet, rings, arcs, moons, magnetic environment, and captured history all interacting. The word hidden fits because most of this system is not visible in a normal image. A thumbnail shows a blue planet. A documentary image may show a storm, but the actual Neptune is not a single object. It is an ecosystem of gravity and weather, built from layers we barely understand. Even the color can deceive us. Neptune's blue appearance comes largely from methane-absorbing red light, but color alone does not tell us the whole composition. Uranus also contains methane and appears blue-green, yet Neptune's color and weather look different. Scientists have debated what additional haze, atmospheric structure, or unknown absorbers may influence the exact shade. A planet can be famous for its color, while the reason for that color remains partly unresolved. That is typical of Neptune. The more obvious something seems, the more complicated it becomes when examined closely. Blue does not mean simple. Cold does not mean dead. Far away does not mean disconnected. Smooth does not mean calm. Under the visible clouds, methane is only part of the story. Hydrogen and helium dominate the outer atmosphere. Deeper down, heavier compounds become more important. Water, ammonia, and methane may exist under conditions that transform them into strange phases. Some models suggest layers where materials conduct electricity and contribute to the magnetic field. Others explore whether diamond rain could form under high pressure from carbon-bearing compounds, though the exact interior processes remain uncertain. The important point is not to turn Neptune into a cartoon of diamonds falling through blue gas. The important point is that pressure changes matter. Chemistry changes matter. Matter under planetary conditions can behave in ways that are not intuitive at room temperature on Earth. Neptune is a laboratory the size of a planet, running an experiment we cannot reproduce completely. Inside that laboratory, ordinary boundaries blur. Gas becomes fluid. Ice becomes something more exotic than ice. Heat moves slowly through immense layers. Conducting materials may flow in shells. Magnetic fields rise from invisible currents. Above all of it, winds whip around the planet at incredible speeds, while clouds appear, vanish, and return on cycles still being understood. This is what Neptune is hiding. Not one secret, but many connected secrets. The first secret is a weather engine. Below that sits an interior structure we cannot yet map. Deeper still, a tilted magnetic generator points to strange conducting layers. The Moon system preserves a history of capture and disruption. Its orbit links Neptune to the outer solar system. And far ahead, Triton's orbit may end in destruction. Taken separately, each mystery is fascinating. Together, they make Neptune one of the most important worlds we have barely explored. The reason that matters goes beyond Neptune itself. Across the galaxy, planets in the size range of Neptune and smaller sub-Neptunes appear to be extremely common. Astronomers have discovered many worlds larger than Earth, but smaller than Neptune, a class our own solar system does not contain. Some may have thick hydrogen atmospheres. Others may be water-rich. Some may be rocky planets wrapped in gas. From far away, these planets are hard to classify because we often know only their size, mass, orbit, and sometimes a little about their atmosphere. To understand those distant worlds, we need to understand the closest examples of the family. Uranus and Neptune are the only ice giants we can study in detail from our solar system. Yet, they are also the least explored major planets. That is a strange situation. Some of the most common planet types in the galaxy may be related to the category we understand least from up close. Neptune, therefore, becomes more than a planet at the edge of our Sun's system. It becomes a reference point for interpreting other systems. When astronomers study a blue Neptune-sized exoplanet around another star, they are not only asking what that distant world is like, they are also testing how well we understand our own Neptune. If our local ice giant still hides major secrets, then distant Neptune-like planets may be even more mysterious than we realize. Imagine trying to understand the weather of an exoplanet when Neptune's own weather can still surprise us. Imagine interpreting the atmosphere of a mini Neptune when the deep structure of Neptune remains uncertain. Imagine building models of planetary magnetic fields while the ice giants in our solar system have strange tilted offset fields that do not match simple expectations. The problem scales outward. A mystery in our backyard becomes a mystery across the galaxy. This is why Neptune should not be treated as just the final stop in a tour of the planets. It may be one of the keys to understanding what planets usually become. Earth is precious, but Earth-like worlds may not be the most common. Jupiter is massive, but Jupiter-like giants are not the whole story. Between small rocky worlds and huge gas giants lies a wide territory of planetary possibility. Neptune sits in that territory, cold and distant, holding clues about what happens when a planet grows large enough to keep a thick atmosphere, but not large enough to become a true gas giant. The galaxy may be filled with versions of this question. How do such planets form? How much gas do they capture? How much water and rock do they contain? How do their atmospheres change over billions of years? What happens if they orbit close to their stars, where radiation can strip away gas? What happens if they remain far out, cold and dim, like Neptune? These questions affect the search for habitable worlds too. A planet slightly larger than Earth could be a rocky super-Earth, a water world, or a mini Neptune with a thick atmosphere and no accessible surface. From a distance, the difference can be hard to determine. Understanding the physics of Neptune-like planets helps astronomers avoid mistaking one kind of world for another. Neptune, then, is not only terrifying because of what it is terrifying because of what it represents. The possibility that many planets are harder to read than we want them to be. Size alone can still hide a world's nature. Reflected light may reveal color while concealing the layers below. For billions of years, a planet can orbit quietly while keeping its most important parts buried beyond our instruments. This is not a failure of science. It is the condition that makes science necessary. Neptune reminds us that discovery does not end with naming. A planet can be discovered in 1846, photographed in 1989, monitored for decades, imaged by Webb, and still remain unfinished in our understanding. That is humbling. The discovery of Neptune itself is often told as a triumph of mathematics. Astronomers noticed that Uranus was not moving exactly as expected. Calculations suggested another planet might be tugging on it. Neptune was then found close to where predictions said it should be. In that sense, Neptune entered human knowledge as an invisible influence before it became a visible world. That origin story still feels appropriate. Neptune is a planet of hidden effects. First, its gravity betrayed its existence. Later, its atmosphere betrayed hidden heat. Its magnetic field betrayed hidden interiors. Triton's orbit betrayed a captured past. Its rings betrayed unseen sculpting. Its changing clouds betrayed a connection to the distant sun. Neptune keeps revealing itself indirectly. Almost everything important about it is learned through consequences. A wobble in Uranus, a dark feature in clouds, a tilted magnetic field, a retrograde moon, a clumped ring arc, a fading cloud layer, a bright infrared ring in Webb's view. Each clue points to something underneath, behind, or before the image. That makes Neptune a perfect planet for a question like this title. It is hiding something, but the thing hidden is not a single object waiting to be photographed. The hidden thing is the full truth of how the planet works. And yes, that can be terrifying. Not because Neptune is dangerous to us right now. It is too far away to threaten Earth. Its winds will never touch our cities. Triton's future destruction will not disturb our oceans. Its rings will not fall into our sky. But terror in astronomy is not always personal danger. It can come from scale, from ignorance, and from the realization that even nearby worlds are deeper than our minds expect. Neptune is terrifying in that way. A calm image hides a violent system. Another unease comes from the fact that we have barely visited this planet, despite living in the same solar system. Time adds its own darkness. Moons can be captured, systems can be shattered, storms can vanish, and futures can unfold over millions or billions of years. Uncertainty completes the feeling. Models, observations, and explanations have brought us far, but the planet remains partly sealed until a spacecraft enters orbit around Neptune, watches it for years, maps its magnetic field, studies its rings, measures its atmosphere, and flies past Triton again and again. The deepest answers will remain out of reach. A Neptune orbiter would change everything. Such a spacecraft could watch dark spots form and die instead of catching isolated snapshots. Long-term tracking would measure winds over months and years. Thermal maps could reveal where heat rises. Spectrometers would follow cloud chemistry. Close magnetic measurements might show whether the dynamo really comes from a strange internal shell. From different angles, the rings and arcs could be examined as dust shifts over time. Repeated Triton flybys would search for active plumes, surface changes, and clues to any hidden ocean or internal activity. Such a mission would not merely add details to a textbook. It would connect scattered mysteries into one system. The lack of that mission is why Neptune still feels like an unfinished chapter. Human beings have sent orbiters to Mars, Jupiter, and Saturn. We have landed on Venus, Mars, Titan, asteroids, and comets. We have flown past Pluto, yet Neptune, a major planet, has only been visited once, quickly, by a spacecraft that could not stay. The flyby was heroic, but brief. Voyager 2 approached, revealed a world of storms, rings, and moons, then moved onward into the dark. Since then, every discovery has had to reach across billions of kilometers. That distance has not stopped science, but it has limited it. Telescopes can see a great deal. They cannot replace being there. This is why the future of Neptune exploration matters. The planet is not a side quest. It is a missing piece of planetary science. It connects solar system history, atmospheric physics, magnetic fields, ring dynamics, moon capture, cryovolcanism, and exoplanet interpretation. Few worlds combine so many questions in one place. When people imagine the most terrifying planet, they often choose Venus because of its crushing heat, or Jupiter because of its size, or a rogue planet drifting through interstellar darkness. Those are strong choices. Venus is hellish. Jupiter is enormous. Rogue planets are lonely and strange. Neptune's fear is quieter. It does not scream. It waits. It sits far out in dim sunlight, blue and almost peaceful, while winds race through its atmosphere faster than anything on Earth. Its storms form and disappear. Its clouds respond to a sun that barely warms it. Its magnetic field tilts strangely through space. Its largest moon circles backward, a captured world with geysers on a surface colder than imagination. Its rings contain arcs that should not be so neatly clumped. Its system may still be evolving toward a distant catastrophe. A quiet planet can be the most unsettling one, because quiet makes us lower our guard. The greatest trick Neptune plays on the human mind is visual simplicity. It looks like a blue marble at the edge of the solar system. Smooth, distant, cold, almost decorative. That image is easy to file away. The brain says, gas giant, outer planet, far away, done. The science says otherwise. Behind that blue disk is a planet with active weather, incomplete explanations, and a moon that may have been stolen from the outer solar system. It also preserves a record of planetary migration and gravitational disruption. In a larger sense, the same blue disk is a clue to countless planets beyond the Sun. The more we learn, the less Neptune feels like the end of the solar system. It feels more like a doorway. it opens toward the Kuiper Belt. Captured worlds pass through that same story. Ice giant interiors wait behind another door. And beyond all of that are the common planet types we still struggle to understand. And perhaps most importantly, a doorway to humility. Because Neptune tells us that distance is not the only barrier in astronomy. Sometimes, the barrier is assumption. A name can make a planet feel understood. A category can make the object inside it seem solved. A photograph can feel like knowledge. Neptune breaks those assumptions gently, then completely. A name is not understanding. A color is not understanding. A flyby is not understanding. Even decades of observation are not the same as knowing a world from the inside out. This is the feeling that should remain at the end of the story. Neptune is not just hiding something from us, it is teaching us how much can be hidden in plain sight. The dark spots are visible, but their deeper mechanics are uncertain. The clouds are visible, but their long-term cycles remain complex. The rings are visible, but the arcs still need explanation. Triton is visible, but its origin and interior remain rich with unanswered questions. The magnetic field is measurable, but the dynamo that creates it is buried in an exotic interior. The planet itself is visible, but the world beneath the blue light remains mostly inaccessible. Every answer opens a lower layer. That is what makes Neptune worth returning to. Beauty is part of it, and distance adds drama. Storms, rings, and moons would each justify attention on their own. But Neptune matters most because it is one of the few places where our ignorance is still large enough to be exciting. There are worlds we study to confirm what we already know. Neptune is a world we study because it may show us what we have missed. A future spacecraft could arrive and find that some of our models were close. It could also find something unexpected, a different internal structure, a more active Triton, ring arcs changing faster than predicted, cloud cycles tied to chemistry in ways we have not modeled, or magnetic behavior that forces a new picture of ice giant interiors. The best missions do that. They do not simply fill blanks. They change the shape of the questions. Voyager did this once. Before Voyager 2, Neptune was a distant dot with estimates, hints, and guesses. After Voyager, it became a real place with storms, rings, moons, and a face. An orbiter could do the same at a higher level. It could turn Neptune from a glimpsed world into a known system. Until then, the planet remains suspended between knowledge and mystery. We know enough to be amazed. We do not know enough to be comfortable. That balance is the heart of Neptune. Neptune feels familiar because it belongs to our solar system, yet alien because its workings remain so strange. In cosmic terms, it is close enough for machines to reach, while still far enough to demand a generational effort. Telescopes can monitor it, but every observation requires care. A child can recognize it as the blue planet. Specialists can spend careers trying to understand what that blue planet is doing. Maybe that is why Neptune works so well as the final major planet. Not because it finishes the story, but because it refuses to finish it. Beyond Neptune, the solar system does not end. It dissolves into icy bodies, dwarf planets, resonant orbits, scattered objects, and eventually the distant influence of the Sun fading into interstellar space. Neptune marks the last giant before that transition. It is the final enormous planet before the architecture becomes colder, smaller, and more dispersed. A boundary world should be mysterious. Neptune is exactly that. It stands at the edge of the old planetary map, holding a captured moon from the realm beyond, wearing rings that are faint and fractured, turning with a magnetic field that does not line up, shining blue from methane, while hiding an interior no one has entered. It is both part of the known solar system and a preview of the unknown one. The title says Neptune is hiding something. By now, the better answer is that Neptune is hiding almost everything that matters most. Its visible face is only the invitation. The storms tell us the atmosphere is alive. The disappearing clouds tell us distant sunlight still matters. The internal heat tells us the planet's formation is not finished in a thermal sense. The magnetic field tells us exotic fluids may be moving deep inside. Triton tells us the system has been violently rearranged. The rings tell us small particles and moons are still engaged in a delicate gravitational dance. The exoplanet connection tells us Neptune may be a local clue to a galactic population. None of those secrets requires exaggeration. Reality is strange enough. If we could hover above Neptune's cloud tops, there would be no surface below us, only depth. The sky would not feel like Earth's sky. The sun would be small and weak. Beneath us, blue layers would descend into pressure and darkness. Winds would race around the planet. Far away, Triton would move backward through its orbit, pale and cold, carrying frozen nitrogen and traces of activity. Faint rings would circle in dusty arcs. The whole system would seem quiet from a distance, but every part of it would be moving, evolving, and concealing something. That is the image to keep. Not Neptune as a simple blue ball. Neptune as a cold machine at the edge of the sun's domain. A machine powered by old heat, shaped by gravity, disturbed by captured worlds, and watched from far away by a species that has only flown past it once. The terrifying part is not that Neptune wants anything. Planets do not want. They do not threaten or hide with intention. The terror comes from our perspective. We are small, temporary observers looking at a vast natural system that does not simplify itself for us. Neptune does not explain itself. It only shows clues. A dark spot appears, a cloud field fades, a moon erupts, a ring arc holds together, a magnetic field tilts away from expectation. Each clue asks us to look again. And perhaps that is the real reason Neptune matters. It reminds us that the solar system is not a museum of finished objects. It is active. It has weather, movement, violence, chemistry, and memory. Even at its cold edge, worlds are changing. The sun's family is not still. Neptune proves that. A planet can sit in dim light for billions of years and still have storms. A moon can freeze under faint sunlight and still erupt. Rings can circle in darkness and still form patterns. Ancient captures can still shape the present. Hidden interiors can still influence space around them. So when we ask what Neptune is hiding, we are really asking a larger question. How much of any world do we truly see? For Earth, we live on the surface and still struggle to understand the deep mantle, the core, the climate, the oceans, and the long future. For Neptune, we do not even have that intimacy. We have light, gravity, magnetism, and one flyby. That is enough to begin the story, not finish it. The same will be true for countless worlds beyond the solar system. A dot of light may hide oceans, storms, deserts, ice, magnetic fields, rings, moons, or nothing at all. A transit curve may hide a planet's entire history. A spectrum may hint at chemicals while leaving the deeper structure unknown. Neptune prepares us for that humility. It teaches us not to trust the surface of a planet too quickly. It teaches us not to confuse category with knowledge. Most of all, it teaches us that the universe can place mystery not only in black holes, distant galaxies, or the first moments after the Big Bang, but in a blue planet already listed in every textbook. Neptune is not unknown because it is beyond imagination. It is unknown because we have not gone back. That may be the most frustrating and exciting part of all. This is not a mystery locked forever behind physics. It is not beyond the horizon of the observable universe. It is not sealed inside a singularity. Neptune is reachable. Difficult? Yes. Expensive? Yes. Slow? Yes. But reachable. A future mission could go there. A future generation could watch the storms directly, map the rings, and return to Triton. One day, the blue planet at the edge may stop being a brief encounter and become a place we study continuously. Until that day, Neptune remains a warning written in pale blue light. Never assume the quiet world is simple. Distance does not mean stillness. One spacecraft passing by does not mean a planet has given up its secrets. The mystery is still there, turning slowly in the dark. And somewhere beneath those clouds, below the visible blue, inside layers of pressure, heat, strange chemistry, and hidden motion, Neptune is still doing what it has done for billions of years. It is keeping its secrets, for now. And that is why Neptune is not just beautiful, it is terrifying. The strangest part of studying Neptune is that every major answer seems to split into several smaller questions. The winds point to heat, but heat points to the interior. The interior points to magnetic fields, but the magnetic field points to fluids we cannot sample. Triton points to capture, but capture points to a lost system of moons we may never reconstruct completely. The rings point to resonances, but resonances point to tiny moons and dust dynamics that change over time. Neptune is not a puzzle with one missing piece. It is a puzzle where the picture on the box was never printed clearly. This is also why the planet rewards patience. A single image can mislead. A single year can look ordinary. Only long records reveal the rhythm. Hubble's decades of observations matter because Neptune does not expose all of its behavior at once. A storm may form between visits. A cloud band may fade slowly. A bright region may return after a delay. A ring arc may change over decades. Time itself becomes one of the instruments needed to study the planet. That is difficult for human attention. We like discoveries that arrive in a clean moment. One image, one announcement, one headline. Neptune works more quietly. It gives a clue, waits years, changes, and then forces scientists to compare the new view with the old one. Its mysteries are not only deep in space, they are spread across time. Even the word terrifying should be understood in that slower way. Neptune is not terrifying like an explosion. It is terrifying like deep water seen from above, when the surface looks calm but the depth is unknown. It is terrifying like a locked door in a familiar house. The fear comes from realizing that the familiar thing was never fully familiar at all. A future mission would need patience too. An orbiter could not solve everything in a single flyby. It would have to watch seasons that last for decades, storms that evolve over months or years, and moons that change subtly. It would have to listen to the planet's magnetic environment, track ring particles, and return to Triton repeatedly. The reward would be a transformation in how we understand ice giants, but the work would be slow, careful, and long. That kind of science fits Neptune. Fast answers do not belong to a world where 1 year lasts 165 Earth years. Human lives are short beside the planet's seasons. A cloud cycle, a ring change, or a moon's gradual orbital evolution may require records passed from one generation of scientists to the next. Neptune forces astronomy to think beyond the speed of a headline. Perhaps that is why it remains emotionally powerful. It is both near and unreachable, known and unknown, beautiful and severe. A person can look at a telescope image and understand immediately that Neptune is a planet. Then the deeper facts arrive, one by one, and the simple image collapses into something larger. The blue disk becomes a storm system, a magnetic engine, a graveyard of old orbits, and a clue to planets we have not even named yet. In that sense, Neptune is not hiding because it is dark. It is hiding because nature often works in layers. The visible layer is never the whole object. The same is true for stars, galaxies, black holes, and the universe itself. Light gives us information, but it also gives us surfaces. Science begins when we ask what those surfaces are concealing. Neptune's surface is not solid ground. Its surface is appearance. And appearance is the one thing planets are very good at offering from a distance. They show us color, brightness, motion, and shadow. Beneath that, the real structure waits for mathematics, instruments, patience, and sometimes a spacecraft brave enough to cross the dark. Until then, every new observation is a message from a world that cannot be reduced to its image. That message is clear. The outer solar system is active, the ice giants matter, and the last major planet is not an afterthought. Neptune is one of the least understood large worlds we have, and it may be the best nearby example of a planetary class that fills the galaxy. Another hidden piece is the question of how Neptune formed in the first place. Building a giant planet so far from the Sun is not simple. The young solar system contained gas and dust in a disk, but that disk did not last forever. Giant planets had to gather their material before the gas dispersed. How Uranus and Neptune acquired their masses, why they ended up where they are, and how their migration shaped the outer solar system remain active questions. Neptune is not only hard to understand now. Its birth was difficult too. Some models suggest that the giant planets did not form exactly where we see them today. Their orbits may have shifted as they interacted with the disk of leftover planetesimals. Such migration could have stirred the Kuiper belt, scattered icy bodies, and created resonant populations that still preserve evidence of that ancient movement. In that story, Neptune is not passive. It is one of the sculptors of the outer solar system. This gives Triton even more weight. A captured moon around a migrating ice giant is not just an oddity. It is a witness. It may preserve clues from a time when the outer solar system was crowded with icy worlds and unstable orbits. Its surface, composition, and activity could help connect Neptune to the reservoir of bodies beyond it. Studying Triton is partly studying a lost world from the Kuiper belt that survived by being taken. The smaller moons add another layer. Neptune has a collection of inner moons moving among and near the rings, plus more distant irregular moons with strange orbits. Their arrangement may record collisions, captures, and disruptions. Some could be fragments from older events. Others may have formed from debris after Triton's arrival. A moon system can be a fossil record, but reading it requires getting close enough to see the details. From Earth, those details are painfully hard to obtain. Neptune's distance turns small moons into faint points. Rings become thin traces. Storms blur into patches of brightness. The planet's disk is tiny compared with the giants closer to us. Every telescope observation is an achievement, but also a reminder of how much information is being compressed into a few pixels. That compression changes our emotional relationship with the planet. The image looks simple because distance has erased complexity. If Earth were viewed from Neptune, our own world would lose its mountains, storms, cities, forests, and oceans into a point of light. Neptune has suffered the same flattening in our imagination. It appears simple because we are far away. A spacecraft would restore complexity. It would reveal small waves in clouds, textures in storms, color differences in hazes, details in ring particles, fractures and planes on Triton, and interactions between moons and dust. Distance turns worlds into symbols. Exploration turns them back into places. This is why Neptune still deserves wonder after all the famous discoveries elsewhere. Mars has landscapes. Saturn has rings. Jupiter has the Great Red Spot and ocean moons. Pluto has mountains of ice. Neptune has been quieter in public imagination because it has not received a long mission. The lack of attention is not evidence that the planet is boring. It is evidence that we have not stayed long enough. The greatest unknowns may not even be the ones already named. Before Voyager reached Neptune, no one knew exactly what it would find. The same would be true for an orbiter. Scientists can list expected targets, but the most important results might come from surprises. A storm structure no one predicted, unexpected chemistry on Triton, unexplained ring changes, or measurements of the interior that force old models to be rewritten. That is always the risk and reward of visiting a real world. Models prepare us, but reality edits the models. Neptune has already done this once. It can do it again. This is why the phrase ice giant should feel less like a label and more like a warning. It tells us the planet belongs to a class, but the class itself is not fully understood. Ice giants are not simple stepping stones between rocky worlds and gas giants. They have their own physics, their own histories, and their own ways of hiding information. Neptune is the clearest example we have, and even this clearest example is still dimmed by distance. Consider the atmosphere again from the point of view of a future probe. At the top, instruments might taste methane, hydrogen, helium, and hazes shaped by ultraviolet light. Deeper down, pressure would rise until no spacecraft could continue for long. Temperatures would climb. Signals would weaken. Before the probe was destroyed or silenced, it might send back measurements that changed our models forever. A few minutes inside Neptune could teach us more than decades of guessing from far away. That is not because remote astronomy is weak. It is because planets are layered objects. Telescopes are extraordinary at seeing light, temperature, composition, motion, and change from a distance. But a planet's deepest truths often live below the levels where light escapes cleanly. To reach them, science needs more than images. It needs gravity measurements, magnetic measurements, atmospheric sampling, long-term monitoring, and sometimes the courage to send a machine into a place it cannot survive. Neptune has never received that kind of sacrifice. No probe has fallen through its sky. No orbiter has listened to its magnetic field for years. No spacecraft has watched a dark spot from birth to disappearance. No mission has mapped Triton season after season. The planet remains almost untouched by direct exploration, which is astonishing when we remember that it is not an exoplanet. It is part of our own system. If you listened this far, thank you for spending this quiet journey at the edge of the solar system. Subscribe to Just About Space for more calm explorations of the universe. Leave a like if this video made Neptune feel stranger than before, and write a comment telling us which part of the planet feels most mysterious to you. The storms, Triton, the rings, or the hidden interior. Because the next time you see Neptune as a small blue dot, remember what that dot contains: a world with supersonic winds, a sky that changes with the distant sun, a captured moon that erupts in the cold, rings that clump where they should spread, a magnetic field that refuses to point where expected, and a future still waiting in the dark. Neptune is hiding something. Not one thing, a whole planet's worth of them.